Okay, so now in this next video, let's not learn about the Greek alphabet, although we are going to use alpha, beta, and gamma, but let's explore alpha, beta, and gamma decay in a little more detail. So let's explore alpha decay in a little bit more detail now. We'll start in the middle here, I think. So essentially what happens is we start off with some parent nucleus, and as I said, these are alpha decay the ones normally with an atomic number greater than 83, and that decays to a daughter nucleus which has 2 less protons and 2 less neutrons, so a mass number of 4 less. That mass number is lost as an alpha particle, and we'll talk about this particle that's also released in a sec. So a specific example of that might be one that's been in the news because of being used to kill Russian spies is polonium-210, atomic number 84. That will undergo alpha decay, and it will form a nucleus with an atomic number of 82, so 2 less, and a mass number of 206. Now 82, if we look on a periodic table, is lead. Those 2 protons and 2 neutrons are lost as an alpha particle, and when this alpha particle, when this daughter nucleus forms, it will be in an excited state. It's not just its electrons in an excited state, its actual nucleus will be in excited state. A nucleus has energy levels within it, just like there is energy levels within an electron, but there's much greater differences between the energy levels in the nucleus. They're normally on a mega electron volt scale, whereas the energy levels in the electrons are usually on an electron volt scale. So when this nucleus relaxes, we get the release of a gamma photon, just in the same way as we get maybe a visible or a UV or an infrared photon released when a normal atom relaxes. I'm going to talk about this in a couple of slides more in detail, and I've got a graphic on this that I couldn't really fit here, so we will come back to that. Now, also, we just need to be aware that the alpha particle also will be released with what we call discrete, or a certain number of discrete or fixed energies, and that is because, once again, we have energy levels within our parent and our daughter nucleus. So when they go from one energy level to another, there is a fixed number of energy level differences we can have there, and those energy levels differences, that energy that's lost between those fixed levels will be transferred to the alpha particle. So it must have one of those fixed ones. I think when we look at the graphic of energy levels in the nucleus in a couple more slides, hopefully that will make some more sense. But this is the really important thing to remember here in the middle. That is basically the equation, the general equation, and a specific example for alpha decay. Okay, so now let's look at beta minus decay in some more detail. So beta minus decay occurs when a nucleus has an excess of neutrons and involves the conversion of a neutron into a proton. And we're going to talk about some of the other things that happen. But essentially at its core, we have a neutron that gets to a proton. Obviously, to conserve charge, we need to have also an electron emitted, because a proton plus 1 charge, an electron has a negative charge, that gives us a 0 overall charge, which just matches a neutron. When scientists, though, first started studying beta minus decay, they may be expected in the same way that the alpha particle has discrete energy levels that correspond to energy level differences between the parent and daughter nucleus. They found that they had a whole range of energies and momentum up to some maximum. And this had some important implications, and we're going to explore those in 1 second. They also found after beta decay, the nucleus is left in an excited state, and this decays to the ground state by emitting a gamma ray. So in the same way that the daughter nucleus in alpha decay can be in an excited state, relaxes, releasing a high energy photon, same thing here. We'll talk a little bit more about the detail of this, as I said before, at the end. But you'll see here we've introduced this new particle here, the anti-neutrino. So when scientists studied this reaction, there was basically some missing energy. So firstly, the electrons didn't have a discrete amount of energy, but also, like there was a continuous range, but also observing the particle's release could not explain all the energy and momentum of everything was observed. So what they did is they proposed there must be another particle released called an anti-neutrino. Now, they then went away and looked, and it took several years, possibly even decades, and eventually they detected this presence of this neutrino. This neutrino is very, very hard to detect because it doesn't have any significant mass and it doesn't have any charge. So that means it doesn't really interact with any type of matter in the same way that most particles would interact with matter. This isn't great physics, but you can almost think of it like an electron with no charge. So we've talked about a positron, which is a positively charged electron, a normal electron, which is negatively charged. The neutrino is a little bit like, or an antineutrino, an electron that doesn't have any charge. And basically, because it has very little charge or no charge or mass, it was very hard to detect. But eventually they were able to detect it. So, I think basically what I've just said there explains everything that is said in those two paragraphs there. And as we said, we go back here to the gamma. The daughter nucleus also has a finite amount of energy. So I think it's just worth to finish off here. Let's look at a specific equation for beta minus decay. So one of the most common examples, this is used in carbon dating, is carbon 14. So it's got 8 neutrons, 6 protons, so it's an excess of neutrons. And then when that undergoes decay, one neutron is converted to a proton, so we end up with 7 protons. We now have 7 protons and 7 neutrons, so the number of nucleons doesn't change, so the mass number doesn't change. So that becomes nitrogen, because nitrogen is the atom that has 7 protons, and we get the release of... Now, I tend to write the beta minus particle like that rather than as an electron, but either is acceptable. Then because it's beta minus decay, we get the anti-neutrino, and that line across the top indicates an anti-neutrino. When we talk about beta plus decay in a sec, we'll talk about the neutrino, and we also get the gamma ray photon. So there is a specific example of our generalized equation for beta minus decay. And in a very similar sense to beta minus decay, where we have an excess of protons, we can get the conversion of a proton into a neutron. This is accompanied by the emission of a positron to conserve charge. Now, instead of getting an antineutrino to explain conservation of momentum and energy, we get a neutrino. So basically very, very similar to what we just talked about. We start off with a parent, but now we lose a proton because a proton is converted to a neutron. We get a beta plus or a positron released, a neutrino, and a gamma ray photon. So just to give a specific example of that, and this is one that we will talk about probably again with our application. Oxygen 15 So you would expect oxygen in that first 20, so you'd expect a 1-to-1 ratio of protons to neutrons, so a number of nucleons would be 16, 8 protons, 8 neutrons. So we can see this one's sort of lacking a neutron, so it's got not enough neutrons or too many protons, either way you want to think about it. So this loses a proton, so we go back to 7, the atomic number stays the same. Because it's 7, it's nitrogen again. We get the beta plus particle. As I said, you can write that as a positron, or you can write it like that, doesn't matter. Plus we get our neutrino, so no line on top because this is the neutrino, not the antineutrino. And we also get our gamma ray photon. Now, we'll come back to this later, but this positron that's produced here will often collide with an electron. So this positron here will collide with an electron, and they will annihilate each other, so they will be completely destroyed, and their mass will be converted into energy using the E=mc² type equation that we saw in the last relationship. And this has some really important medical applications which we will explore in the application of this topic when we get to the end. So I just want to finish by talking a little bit more about the energy levels within the nucleus as opposed to the atom, and basically what happens with gamma decay. So we've talked that with alpha and beta decay we also get gamma decay. So after alpha or beta decay, a nucleus is sometimes left in a small number of possible excited states, often indicated with a star. Such a nucleus decays to the ground state by emitting one or more high-energy photons or gamma rays, in the same way that when an atom relaxes, it releases a photon, but not a super high-energy photon. So the general equation of gamma decay is here. Obviously, N is the number of high-energy photons emitted. So sort of what does this look like in terms of the energy? So let's think about here, and this would be an example of beta minus decay. You've got a magnesium here, magnesium 27, undergoes beta minus decay to form aluminium 27. Now, because the magnesium nucleus has a certain energy level and the aluminium has certain energy levels, when this relaxes, the beta particle will get an energy corresponding to this transition from this state to this state, or this state to this state. So in this case, there'd be two possible energies of the beta particle. The same would apply if this had been something that undergoes alpha decay. Obviously, the atomic number would have been greater than 82. It would have been bigger. And this energy here would go to the alpha particle rather than the beta particle. So that's, if you like, the energy of our beta or our alpha particle. However, the daughter nucleus then will be possibly in an excited state, and when it decays, it can release the gamma ray photons, and as you can see here, there are three possible energies that the gamma ray photon would have, corresponding to the three possible energy transitions within the nucleus. And as I said before, we can see these are on a mega electron volt scale, these sort of energy levels. Whereas when we looked at the structure of the atom, we saw, when we talk about electrons, so not the energy levels in the nucleus, but the energy levels of the electrons, they're usually only on an electron volt scale.